we are talking about there will be harmonics there will be harmonics in the system. So these harmonics can be reduced. We need to reduce these harmonics. Okay, we need these are unwanted signals. So to reduce these harmonic signals, reduce the harmonics. So there are different ways like pulse width modulations, or the harmonic reduction transformers, or can be step wave inverters. There are different way of reducing the harmonics. So these are the unwanted signals. So whenever we are converting from one form to another, there will be unwanted signals, or we call as a harmonics, or in a system. So what we require is a pure AC, okay, and the input is a DC. Should be a pure, should be a DC.
Current is constant but adjustable. The amplitude of output current from SCI is independent of the load. However, the magnitude of output voltage in its waveform output from
Can you please switch off here? I think some of you, I don't know. Participate. Okay. Now we'll see this in last class. We have seen the BSI, the voltage source inverter. Now we'll see what is CSI, current source inverter. Okay. In this case, in current source inverter, means input currents can be is constant, but it can be adjusted. It can be adjustable. So to put this input current constant, okay, then it's like the amplitude of the output current is independent of the load. So it's independent of the load, but the magnitude of the output voltage and its waveform from the CSI is dependent on the nature of the load impedance. So it depends on the nature of the load impedance. So these CSIs are used in the application part. It is used in a speed control of the AC motors, induction heatings, okay, lagging power compensations, and this can be used in a synchronous motor starting also. So CSI can be, there are so many applications, okay, where CSIs are used. Now if you see, this is a idle CSI, okay, current source inverter. So in this first portion, okay, is a current source, okay, you have input is a E and the large inductance. So what is the function of this inductance is to have a constant current, constant input current. So your CSI it contains this CSI contains a 4 thyristors. These 2 thyristors are fired together, T1 and T2, and alternatively in another half T3 and T4s are fired. And the load contains means load can be a resistive load, it can be a RL load, so that depends on a different type of load. So these CSIs are, so we assume that thyristor we assume as an idle switch with the 0 commutation times. So positive directions of voltage and currents are indicated. So this is positive direction, so it is indicated in the figure. So voltage and currents are indicated here, and the source consists of the source voltage source E and the large inductance in series. So that is to function as a high impedance reactor in series with the voltage source. So to maintain this is to maintain the constant current in input terminal of the CSI. So the current should be constant at the input terminal. That's why the large inductance is, is there. It consists of the voltage source with the large inductance L in series. So this is mainly to have a constant. These two, okay, this inductance, large inductance is mainly to have a constant current source. So in other words, DC inputs to CSI is constant. So input DC means the input current is constant in this case. So T1 and T2s are own. These T1 and T2s are fired together, and when these two T1 and T2 are on, load current is I naught. This load current is positive, and simultaneously when the T3 and T4s are fired, then the negative load current I naught is negative, which is equals to negative I. So if you see from this waveform, the current is input current is constant. Okay, with the help of high input means inductance in this, the current constant input currents, this input current. Then when T1 and T2 are fired, then the current is positive. When T3 and T4 are fired, the current is means current is negative. Now this is a voltage. Okay, the one full cycle means 0 to t, then it becomes f is equals to 1 by t. Now I just want to ask you this question, that why there is frequency input, the input voltage, the frequency is equals to 2f. So please try to see this. Okay, the frequency is equals to 2f. By seeing this diagram, we can find out that the frequency input frequency is equals to 2f. So output frequency of INO can be varied by controlling the frequency of the triggering of the thyristor pair. So that we have to keep the frequency constant. Means like you have to maintain the frequency. If we are thinking of the, let's say, supply frequency equals to 50 hertz. Now this frequency can be controlled by the frequency of the triggering of the thyristor pair. So we have to know this, that the frequency is depends on the triggering of the SCR of the pair. These are the two pairs which are fired simultaneously, T1 and T2 and T3 and T4. These are the four thyristors. So output current is a square wave of the amplitude equals to the DC input current. So output current will be the equals to the amplitude. So if output current is this, equals to the amplitude of the input DC current. So output current will be the square wave. So this positive from 0 to t by 2. So in this case, the slope is from 0 to t by 2, that goes to the positive. So t by 2 negative from t by 2 to t on the basis where the of the load voltage is drawn. So the input current to the CSI will be V, and input voltage will be equals to the output voltage. So when T1 and T2 are conducting, and when T3 and T4 are conducting, output voltage will be negative V naught. So if you see here, the T3 and T4, it will be a negative V naught. So when T1 and T2 is conducting, it will go to the negative, means like positive V naught. So for f equals to 1 by t, that is the frequency is equals to 1 by total time period. So we know this very well, that as the frequency of the output voltage or the current input voltage has a frequency of 2f. So this statement, okay, the frequency for f equals to, as the frequency of the output voltage is V naught. So the current or the input voltage V in has a frequency. The input voltage will have the frequency of 2f. So this is revealed by the examinations. Okay, so please try to find out that why the input frequency is 2f. Input voltage has a frequency of 2f. So DC input current, okay, DC current. So input to the CSI is a unidirectional nature. So it is a unidirectional because all these, the T1, T2, T3, okay, thyristor, these are the unidirectional in nature. So the average value of the V will be positive. So if the average value of the input voltage is positive, so if the average value of the V in is positive, then the current will flow from the source to load. If the average value is negative, then it's a regenerative of power take place. It means that power will flow from the load to source, not from the source to load. So this is the waveform. So input current is to the CSI, current input to the CSI is constant because of the L, high L. So when T1 and T2 are fired, then the current is positive. When T3 and T4 are fired, the current is negative. So, but the voltage will be positive when, okay, the average voltage will be positive, then the current will flow from source to load. And if the average voltage is negative, then the current will flow from load to source. And the input frequency will be, if you see here, the input frequency is 2 times. If you see here that this is the total time period, 0 to t, then the frequency is 2f, 2 times. Now the other one is single phase capacitor commutative CSI with R load. So load can be R. Now why the name is given as the commutative, means like single phase capacitor commutative CSI, current source inverter, because we need to differentiate all these capacitors means all the CSI requires a capacitor. Just to differentiate this, okay, that the commutations is taken place with the help of the capacitors in this one. So commutations can be possible with with the help of the capacitor in this one. Similarly to that, what we have seen in the previous CSIs. It also has a 4 thyristors. Just to differentiate this, we call as a capacitor commutative CSI. So in this one, the all force commutation CSI needs capacitors actually. Is force commutation will require a capacitors in commutation. So capacitor commutated is used just to distinguish this CSIs from. So just to distinguish the CSIs, okay, just to differentiate between the other CSIs, so it is used as a capacitor commutated CSI. So it has a load as a R load. The source for the inverter is constant, but it can have a stable DC source, current source. So capacitor is in parallel with the load. So this capacitor is in parallel with the load. This capacitor is in parallel with the load in this case. So storage. So what's the function of this capacitor is in parallel with the load? It's used for storage of the charges in force commutating the ACI. So is capacitor used as a storage device. So just to have a charge for the free commutation means post commutation of the ACIs. So in this case, thyristor, there are 4 thyristors. These 4 thyristors are the means power switches. These are the power switches, and they are gated in pair. These are gated in pair. You have to be mindful that these two are gated together. T1 and T2 is gated together, and T3 and T4 is also gated together. So it's gated in a pair. It means that it is triggered together. T1 and T2 is triggered together, and T3 and T4 is gated together. So T1 and T2 is triggered with IG1 and IG2, and T3 and T4 are triggered with IG gate current IG3 and the IG4. Means like in this one, the positive direction for the load current and the load voltage are marked in this case. So similarly, so T at T equals to the capacitor voltage will be VC will be minus V1. So left plate negative and right plate will be positive. Similarly, in this case, T1 and T2 are gated at T equals to 0. So if you see here the waveform, so at this point the output current, it is when T1 and T2 are gated together. So the current will be positive in this case. So similarly, okay, at the other end means like T3 when the T3 are gated together means gated together, then T1 and T will be commutated. Okay, so in this case, so parallel combination of R and C will be through T2. So there will be a commutation immediately. There will be a commutations, and the source current now will flow from T1 when the T3 and T4 are commutated. Similarly, this will happen to what we have seen in the previous case, that this will happen alternatively. T4 and T5 will be T3 and T4 will be commutated. At this point, then with the help of T1 and IT3 and IT4 will be equals to positive pi. So the current, this current will be equals to minus I naught. So similarly, in this case, the current will be minus I naught. So in this case, okay, I naught plus IC will be equals to I. So this is IC plus, okay, this is IC, okay, IAC will be equals to IC plus I naught. IC plus I naught, so IC will be equal to total I minus I naught. So this is the waveform, output means current waveform. So these are the equivalent circuit of when it is from 0 to T by 2, the current will flow in this one. In this case, I will be equal to I naught plus IC plus I naught. So the voltage will be, output voltage will be VC, voltage across the capacitors. Similarly, during the equivalent circuit of T by 2 to T, then the VC will be equals to V naught. Then in this case, if you see, the current is flowing in opposite directions. So this is the waveform where in this case, initially IG1 and IG2 is triggering the T1 and T2. Similarly, in the other half, IG3 and IG4 will be triggered. So this is, so during this spread when T1 and T2 are triggered, and this is the current waveform. So this simultaneously T1 and T2, but in other, when the T1 and T2 are conducting, that T3 and T4 will be commutated. The voltage will be from from negative, it will go from this negative to this positive point. So there one whole cycle will be t, total time 0 to t. So these are the similar whatever we have done previously, okay, just to differentiate between the normal CSI and means capacitor commutative CSI. Because capacitor is mainly used for the commutation purpose, commutation of the SCR. So when the SCR, one set of SCR is conducting, other set of SCR should be commutated. So post commutations are used. So there are similar type of MC Mori inverters are there. Okay, you don't have to submit this as assignment, but please go through this MC Mori inverters. This is quite important. So this is similar to whatever we have seen here. Okay, as CSI, okay, different type of CSI like capacitor commutative CSI or the I2 type of CSI. Okay, that's why I did not. I feel that you can just go through this so you can understand. Okay, it's similar to that whatever we have seen till now. Now next we'll see this pulse width modulation inverter. Now why we require a pulse? Because we have seen a different type of inverter, but there are drawbacks. Okay, whatever we have seen till now is a square wave inverters. It's a square wave inverter. So far, there are certain disadvantages of square wave inverters. So just to overcome this, okay, it has a disadvantage. So disadvantage that for the fixed source the voltage, the output voltage of the inverter cannot be controlled. So you have an input fixed source input, then output has to be controlled. Now, how do we control this output? You require additional circuit, okay, to control the output. Inverters cannot be controlled. Okay, when you have a fixed, if you require a variable output, inverter must be fed either from the controlled AC to DC. So you have to have a control type of regulators, or you need to have a DC to DC converter, or you need to have a input control like DC to DC converter means chopper. So chopper means for main function of a chopper. We have already done this, that the fixed DC will be converted to a variable DC. Also, this is the additional circuit requirement. So this is the drawbacks of a square wave inverter, whatever we have seen till now. So the output voltage contain appreciable harmonics. So in this case, the output voltage, whatever we have seen till now, the square wave inverter contains harmonics. That's why we have seen the harmonics are there in the in. Now to remove this harmonics, we need to have a separate device, means a system where you need to remove these harmonics. Harmonics can be removed, okay, with a harmonic medication transformers, or it can be removed by a pulse width modulations, PWM, pulse width modulation technique. So to achieve the voltage control within the inverter. So if we use a voltage control within the inverter, if you have a system where the output voltage can be controlled within a system, then we can use a pulse width modulations inverters. I have told you in the beginning, sometime back, okay, that what is modulation actually. First thing you have to understand what is modulations and what is pulse width. Width of the pulse can be modulated. So we have seen that even in a chopper, okay, that there is a fixed time period T. Time period T can be modulated, okay, with the help of on and off time. Okay, the width of the pulse can be modulated. So you need to have a carrier signal and a reference signal. So modulation, I have told you, okay, just to refresh you back, okay, the modulation is something modulating a signal, means with the help of if the input signals are weak signals, okay, then these signals has to be modulated with the carrier signal. It's something like you are helping the signal so that it can be modulated, and demodulation means retrieving back to the original signals. So these two terms are quite important for you to understand. Modulation, there are so different type of modulation techniques are there. We call as amplitude modulation, we call as FM frequency modulations. What is the full form of FM? We tune to a radio, okay, that is of frequency modulations. It's just a modulation only. So we call as FM, SW, short wave, or okay, all these are communication terms. So just to understand in this case, okay, the modulation is you are controlling mechanism can be possible. So where we have to depend on the duty cycle, the total time period, and what is the T on time period of that particular switch. So we are using a switch. Switches are, it can be a SCR, it can be a BJT power BJT, it can be a MOSFET, or it can be IGBT. So this can be used as a switches. So how long are we going to switch on these switches, and what is the efficiency of these switches? How frequently you can switch on and off? So pulse width inverters, width of the output pulses are modulated. It means that the width of the pulse, you have one pulse, one cycle, okay, that total time period is t equals to 1 by f. The frequency can also be controlled. So it means that how how long are you going to trigger that means at what is the angle, firing angle. So that will depend on the output frequency, or can also be controlled with this. So output voltage can also be controlled with the limit at what firing angle are you triggering that ACR or that switch. So there are two different types: a single pulse with modulations, where a single pulse is given to a system, and a multiple or uniform pulse with modulation means the width of the pulse is uniform, or you're giving a pulse triggering to the systems. And there are like waveforms, okay, to just to explain, but it's quite difficult for me to draw here and explain you. But later on, if we get time, okay, to face interview, means like I'll try to show you in a waveform, okay, how this multiple pulse means all this digitization, okay. When you talk about the digitization input signals, okay, this it's just a pulse. We're just giving us pulse. It's means like envelope detection, okay. In the modulation, what is happening is that each of the signals, if you try to convert in a digital form, is just 0 and 1. So when you try to retrieve back this original signal, okay, that we call as a demodulating a signal, means like retrieving back to the original signal. So in case of pulse with single pulse with modulation, okay, there are there is a rectangular reference signals, that is AR, and it's compared with the triangular carrier wave. So the carrier wave, the carrier signal is a triangular form, and you have reference signals as a rectangular form. So you have to compare with the reference signals with compare that carrier signals compared with the reference signal. There's only one pulse is valid to control the output. So there's only one pulse. If you see in this diagram, that single pulse is given to the system. So when you trigger this ACR or any power electronics device, okay, when you trigger this, there's only one pulse, means just one trigger is given to a system. So you have to compare this and try to find out the modulating index of a system. So when you find out the means modulation index of the system, okay, the delta is given as the pulse width, means when it changes from the reference signals. So this modulation means you have to this reference signal, it has to be modulated with the reference signals. So carrier signals and the reference signals are both modulated together. It's something like this. Okay, when your grandfather is not able to go to Samjongkar, okay, means he's require some kind of support, like vehicle is some kind of support. So carrier signal is support given to the input signal. So this carrier signals, when you are giving a support to the if weak input signals like a reference signals, so this you're giving a support to a signal, so that your grandfather is able to go to Samjongkar. So the vehicle or a horse, maybe in olden days. Okay. So this is we're just trying to give you some idea, okay, how this carrier signals and the input signals are interrelated. But at the destinations, okay, it has to be retrieved back to the original signals. So when you retrieve back to the original signal, it has to be exactly the same as the input signal. The same thing is happening with the mobile phone or mobile communications or any type of communications. We are sending an input signal. Okay, these signals are all whatever we speak. These are the analog signals. So this has to be converted into a digital form, and at the receiving end, again it has to be retrieved back to the original signal. It has to retrieve back to the analog signals. So this means that there is a communication is going on in the form of a digital 0 and 1 form. But the input is analog. The output should also be analog. But the process going on in between, the modulating and demodulations are taking place in between. So we can find out what is the modulation index based on the carrier signal and the reference signals. AR is the reference signal and EC is the carrier signal. We can find out what is the modulation index of the system. So with the help of this, we can find out the output voltage. So output voltage is equals to V root of delta by pi, root of delta by pi. So if you just integrate this, I know you know the integration. So if you just integrate, you'll find out the output voltage, RMS value of the output voltage, which is equals to VL equals to input voltage P root of delta by pi. So similar to the single pulse with modulation, then we have another multiple pulse with modulation. Means multiple pulse are given to a system. So there are certain disadvantages of a single pulse modulation. This disadvantage of single pulse with modulation is that it contains a harmonics. So to reduce the harmonics, you can use a multiple pulse with modulations. So multiple pulse with modulations that so the main intention here is to control the out means to have a controlled output. Our input is DC, so we need to have a variable output. Just to have a variable output, internally we can adjust. So internal adjustment can be done. The fixed width of the pulse. The width of the pulse can be varied with a multiple pulse given. It's just a triggering, okay? That means that it's some kind of initiating this, just giving a triggering to a system. So number of pulse in each half cycles is equals to mf by 2. So p is the number of pulse. So we can find out the frequency modulation ratio from this, and f naught is the frequency of the output signal. So we can have variation of the ratio of the reference signal with the carrier signals is from 0 to 1, and pulse width will changes from 0 to pi by p. So it's similar to that of single pulse width. Also we can find out the RMS output voltage VL is equals to V root of P delta by pi. So please try to solve this problem. If you know this problem is direct application of the formula. So just to find out the single phase full bridge inverters has a purely resistive load and is controlled by multiple pulse with modulations. Then the width of each pulse is 30° and each half cycle is 5 pulse. So the input voltage is given as 200 volt and you have to find out RMS output voltage pulse with modulation of the output power constant. If the input voltage is increased by 10%, then you have to find out the maximum possible input voltage if the maximum possible pulse width is 35 degrees. So these are just direct application of formula. I have solution also. So you before looking at the solution, you just do it yourself. So these are the solutions. Okay, you just have to find out VL delta then V. I think I'll stop here. Okay. So I think in the next one class we'll complete this unit. So please do this problem. Try to solve yourself. Okay. This is the very simple, just application of formula. You just if you know the formula, you just have to apply this formula. Okay. I'll stop here. Okay. We'll continue next class. I think we have next classes on Tuesday. I think. I'll just take your attendance.